this tutorial, we will explore how to find the line and phase currents at the primary side of a three-phase transformer connected to an unbalanced load. The transformer in question is a 1000 kVA, 11 kV to 0.4 kV, delta-wye transformer. The Y-connected three-phase unbalanced load has impedances of Z equal to J0.5 per unit, CB equal to J0.8 per unit, and ZC equal to J0.3 per unit, all on a 1 million volt amp base. The sequence impedances are given as X0 equals Z equals X2, all equal to J0.1 per unit. The source voltages at the primary side of AB equal to 11 kV at 0 degrees, VBC equal to 11 kV at negative 120 degrees, and VCA equal to 11 kV at 120 degrees. Both the star point of the transformer and the three-phase load are solidly grounded. The goal is to determine the line and phase currents at the primary side. We will proceed with a step-by-step approach. Firstly, convert the load impedances to per unit values on a 1 million volt amp base. The given impedances are Z per unit equals J0.5 per unit, ZB per unit equals J0.8 per unit, and ZC per unit equals J0.3 per unit. Secondly, convert the source voltages to per unit values on a 1 million volt amp base. VAB per unit is equal to 11 kV divided by the square root of 3 multiplied by 11 kV, which simplifies to 1 per unit at 0 degrees. VBC per unit is equal to 11 kV divided by the square root of 3 multiplied by 11 kV, which simplifies to 1 per unit at negative 120 degrees. VCA per unit is equal to 11 kV divided by the square root of 3 multiplied by 11 kV, which simplifies to 1 per unit at 120 degrees. Thirdly, calculate the phase-to-phase impedances on the primary side of the transformer. C0 is equal to J0.1 per unit, Zone is equal to J0.1 per unit, and Z2 is equal to J0.1 per unit. Fourthly, convert the source voltages to phase-to-neutral values. VAB neutral is equal to VAB per unit divided by the square root of 3, which equals 1 divided by the square root of 3 per unit. VBC neutral is equal to VBC per unit divided by the square root of 3, which equals 1 divided by the square root of 3 per unit. VCA neutral is equal to VCA per unit divided by the square root of 3, which equals 1 divided by the square root of 3 per unit. Fifthly, calculate the current injected by each phase of the load. I per unit is equal to VAB neutral divided by Z per unit plus C0, which equals 1 divided by J0.5 plus J0.1 per unit, which simplifies to 0.89 minus J0.26 per unit. I per unit is equal to VBC neutral divided by ZB per unit plus C0, which equals 1 divided by J0.8 plus J0.1 per unit, which simplifies to 0.71 minus J0.29 per unit. IC per unit is equal to VCA neutral divided by ZC per unit plus C0, which equals 1 divided by J0.3 plus J0.1 per unit, which simplifies to 0.94 minus J0.37 per unit. Sixthly, convert the current from per unit values to actual values. I is equal to I per unit multiplied by the square root of 3 multiplied by 1 million volt amps divided by 11 kilovolts, which equals 45.5 amps at negative 16.7 degrees. I is equal to I per unit multiplied by the square root of 3 multiplied by 1 million volt amps divided by 11 kilovolts, which equals 36.4 amps at negative 21.3 degrees. IC is equal to IC per unit multiplied by the square root of 3 multiplied by 1 million volt amps divided by 11 kilovolts, which equals 48.1 amps at negative 23.3 degrees. In conclusion, the line current at the primary side of the transformer is given by I line equals the square root of 3 multiplied by IR, which equals 78.7 amps at negative 16.7 degrees. The phase currents at the primary side of the transformer are negative I equals 45.5 amps at negative 16.7 degrees, negative IB equals 36.4 amps at negative 21.3 degrees, and negative I equals 48.1 amps at negative 23.3 degrees. These are the line and phase currents on the primary side of the delta-wye transformer under the given unbalanced load conditions.